Imagine trying to coordinate a grand symphony across the internet. But every musician has their own watch, right? And the message is telling them when to play. Always delayed, often arriving totally out of order. What happens?
Chaos, basically.
Exactly, chaos. And yet, our digital world, from online gaming to financial transactions, it relies on what feels like perfect coordination. So how do computers, spread all across the globe, truly agree on what time it is? Or maybe even more fundamentally, what happened first? It's definitely not as simple as just checking some universal clock. Hey everyone, welcome to Computer Science Tech Paper Summary. I'm Alex, and I'm always ready to jump into the fascinating stories behind the tech that shapes our world, often hidden away in, well, brilliant research papers like today's.
And I'm Jordan. I'm here to help unpack the elegant logic and, frankly, groundbreaking ideas that make those stories possible. Today, we're taking a deep dive into a paper that really fundamentally reshaped our understanding of time itself in computing.
Yeah, we're talking about Leslie Lamport's seminal 1978 paper, Time, Clocks, and the Ordering of Events in a Distributed System.
That's the one.
Now, okay, 1978 might sound like ancient history in tech terms, right? But trust us, this isn't just some academic history lesson.
Not at all.
This seemingly abstract topic is, and this is no exaggeration, the foundational bedrock for literally everything we do in distributed computing today. We're talking cloud services, massive online gaming platforms,
Distributed databases,
even things like blockchain technology. If you've ever wondered how multiple independent computers, sometimes continents apart, cooperate and agree on anything without some central brain telling them what to do.
Yeah, how do they do that?
Well, this deep dive will offer you a shortcut, a way to understand the core challenges, and a truly brilliant, elegant solution.
Okay, so to really appreciate Lamport's breakthrough, we first need to properly understand the problem he was tackling. What exactly is a distributed system, at least in this context?
Right, what are we talking about here?
The paper defines it pretty clearly. A collection of distinct processes which are spatially separated and which communicate with one another by exchanging messages.
Okay, distinct processes, spatially separated, communicating via messages. So it's not like, different programs running on my laptop where they all share the same memory and clock.
Exactly. These are truly independent entities. Spatially separated is key, and they communicate only by sending messages back and forth.
Each marching to the beat of its own drum, so to speak.
Pretty much. And the really key characteristic that makes it distributed in this specific sense, the thing that separates it from just, say, a multiprocess system on one machine, is this. The message transmission delay is not negligible compared to the time between events in a single process.
Ah, okay. So the time it takes for a message to get from A to B is actually significant compared to how fast A or B can do things locally?
Precisely. That delay is crucial. When Lamport was writing, systems like the ARPANET, the internet's precursor, were prime examples.
Right, the early days.
But it applies just as much today. Think massive cloud data centers, the internet itself, even multi-core processors where different cores essentially act like separate processes communicating. The delay in sending a message across the network, or even between cores on the same chip sometimes, it's significant relative to how quickly individual processes can execute their own instructions.
And this is exactly where our everyday intuition about time just completely breaks down, isn't it?
It really does.
Most of us, we naturally think of events in a nice, neat, linear, chronological order. We're just ingrained with this idea of universal time. Event A happened at 3:15 p.m., event B happened at 3:16 p.m., so A definitely happened before B.
It seems obvious.
It feels obvious. But in a distributed system, that intuitive grasp of what happened first, well, it just falls apart.
So it's not just difficult, it's impossible sometimes. Right. That's the core revelation Lamport identifies. In a distributed system, it's often impossible to definitively say that one of two events occurred first. It's a fundamental challenge baked into the nature of distributed communication. Events can genuinely appear to happen in different orders depending on where you're observing them from within the system.
Okay, let's play with that for a second. An analogy might help. Imagine you're in New York, right? You send a text message to your friend in Los Angeles.
Okay.
Immediately after hitting send, you pick up the phone and call that same friend. Now, because of network routing, weird delays, whatever, it's entirely possible your friend in LA receives your phone call before they get the text message.
Even though you sent the text first.
Exactly. Even though you sent the text first. So from your friend's perspective, the phone call happened first because that's what they observed first. The communication system, the phone network, the internet, it doesn't inherently know about the real-world order involving you picking up the phone. It just processes the messages as they arrive at its different nodes.
The system itself has no built-in mechanism to know that you're sending the text was, in your mind, the first action related to the call. It just sees two incoming things.
Right. It doesn't know the text caused me to think, oh, I should call too.
This leads directly to what Lamport calls the happened before relation. We can write it like A arrow B, meaning A happened before B.
Okay, the arrow means happened before.
And this relation defines only a partial ordering of events.
Partial ordering. Okay, what does that mean in simple terms?
It means some events have a clear causal relationship. One definitely happened before another because, one caused the other or influenced it through a message. But other events are what we call concurrent.
Concurrent, like happening at the same time, or just unrelated.
More like unrelated in a causal sense. It means neither causally affects the other. From the system's perspective, you can't say that one happened before the other based purely on the flow of information within the system. They're independent.
And this is the tricky part, right? Because people, and therefore system designers, often aren't fully aware of this. They build systems assuming this nice linear global timeline.
And then they get surprised by unexpected behavior, synchronization issues, race conditions. All sorts of problems can crop up because of this partial ordering.
You mentioned an airline reservation system earlier as an example. How does this whole partial ordering mess things up there?
Oh, it's a classic example. The system's specification might say something perfectly reasonable, like, a seat is granted only if the request is made before the flight is filled. Sounds simple. Sounds fair.
Yeah, first come, first served.
Right. But now imagine requests for the very last seat are coming in from different terminals around the world. Maybe one from Tokyo, one from London. They're disconnected, except through the airline's network.
And there are delays.
Exactly.
Yeah.
Significant network delays. So how does the system ensure that condition? How does it know which request was truly made first? It's not about checking some perfectly synchronized physical clock because, well, we've established those are problematic.
Right. It's about the observable sequence of events within the system, how those requests are processed. If two requests for that last seat arrive at, say, the central reservation system, which one actually gets it? Which one happened before the other in that chaotic, delayed environment? Defining happened before reliably is the core challenge. You can't just, pick one randomly.
Yeah, you'd have some very unhappy customers.
Yeah.
So, okay, our everyday intuition fails us. Even relying on physical clocks is problematic. How do computers agree on order, then? This seems like a massive hurdle.
It was, and this fundamental challenge is precisely what Lamport set out to solve. But his approach wasn't about building better clocks. It was about fundamentally redefining time itself, at least for the purposes of distributed systems.
Redefining time. Wow, okay.
Yeah. I mean, even if a system tries to use real physical clocks, like the ones on the computer's motherboards, they aren't perfectly accurate. They drift.
Like my watch is always a few minutes off eventually. Exactly. Just usually much smaller drifts for computer clocks, but they still drift. And relying on them introduces big challenges. How do you even verify a system behaved correctly if its correctness depends on some external, imprecise physical time that the system itself can't perfectly control or observe?
Good point. You need to define correctness based on what the system can see.
Precisely. Lamport argues that the specification for a correct system must be given entirely in terms of observable events within the system. Message sends, message receives, local computations, things the system components actually know about.
And this is where Lamport's genius really comes in, right? The conceptual leap.
Absolutely. The breakthrough wasn't trying to make physical clocks perfect or synchronize them perfectly across the globe, which is, well, incredibly hard, if not impossible. His innovation was to define happened before without using physical clocks at all.
Okay.
By focusing purely on the internal events, the sending and receiving of messages, the sequence of actions within a single process, it's like he said, let's define our own internal universe's timeline. Let's base it purely on what our processes know happened because of the information they exchanged, not on some external wobbly stopwatch.
Creating a self-consistent reality within the system.
Exactly. And before this paper, distributed system synchronization was often really ad hoc. People relied on flawed assumptions about shared global time, or they used very complex, sometimes incorrect brute force methods. Lamport provided a rigorous mathematical foundation. He gave us a language and a framework for thinking about causality in these incredibly complex asynchronous environments.
It wasn't just a technical fix. It sounds like it was a whole new way of thinking.
It absolutely was. A fundamental conceptual leap that opened up entirely new ways to design and build reliable distributed applications.
Okay, so if we ditch physical clocks for defining order, and our intuition is flawed, how do we actually build this internal timeline? Where does Lamport start constructing this happened before idea formally?
He starts by formally defining that happened before relation the error we talked about with three simple but really powerful conditions. Let's break them down.
Okay, which honest?
Condition 1. If event A and event B happen in the same process, and A comes before B in that process's execution sequence, then A happened before B. We write it AB.
Okay, that's the easy one. Like on my computer, if I type H, then E, the H event happens before the E event, steps in a sequence.
Exactly. Simple sequential execution within one place. Condition 2. If A is the sending of a message by one process and B is the receipt of that same message by another process, then A happened before B.
Right, the message send causes the message receive. My friend can't receive my text until after I send it. Obvious causality there.
Precisely. It establishes that crucial causal link across different processes. The sender's action enables and precedes the receiver's action.
Makes sense. And the third?
The third rule is transitivity. If A happened before B and B happened before CBC, then A indirectly happened before CC.
So if A causes B and B causes C, then A indirectly caused C down the line, like a chain reaction.
Exactly. If event A leads to a message that causes event B, and event B then leads to another message that causes event C, then A is considered to have happened before C in this causal chain. These three rules together define the smallest relation that captures this notion of potential causality based purely on events and message passing within the system.
Okay, so those three rules define happened before. What about the things that aren't ordered, the concurrent ones?
Right. Any two distinct events, A and B, are defined as concurrent if A does not happen before B. So AB and DB does not happen before A.
Meaning there's no chain of events and messages linking them according to those three rules.
Exactly. Neither causally affects the other based on the information flow within the system. They essentially happen independently, without knowledge of each other, at least from the system's internal perspective.
To really get a handle on this, the paper uses these cool diagrams, right? Space-time diagrams.
Yes, they're incredibly helpful for visualizing this. Imagine a graph. The horizontal direction represents space, basically. The different processes, P1, P2, P3, lined up side by side.
Like different computers or components.
Right. And the vertical direction represents time flowing upwards. So later times are higher up on the diagram than earlier times.
Got it. Space across, time up.
And on this diagram, we draw dots to represent individual events happening within a process. Vertical lines represent the processes themselves, sort of their timeline, marching forward in their own local time.
And the messages.
Messages are drawn as wavy or diagonal lines, going from a send event dot on one process's line to a receive event dot on another process's line. Crucially, these message lines always have to go upwards. Respecting causality, you can't receive a message before it's sent.
Okay, let me try to paint a picture here for everyone listening. Imagine these processes as like vertical timelines, maybe columns in a spreadsheet. Events are just points, dots on those columns. Messages are these wavy lines connecting points between different columns. Now here's the key. If you can trace a path from event A to event B by only moving upwards along the process lines and following the message lines from send to receive.
Always moving forward in time.
Always moving forward in time. Exactly. Then A happened before B. AB? If you can't draw such an upward path connecting them, they might be concurrent.
That's a great way to visualize it. And the paper's figure 1 shows this perfectly. It has events like P3 on process P and Q3 on process Q. They're drawn sort of side by side horizontally.
Does it look like they happen at the same time?
Visually, maybe. But crucially, there's no path of messages and process steps leading from P3 to Q3 or from Q3 to P3. So they are concurrent. Process P, when it executes P3, has absolutely no information about what process Q did at Q3. It can't know until later, maybe at event P4, it receives a message that was sent after Q3.
It's like two people working in separate rooms. What one person does, Q3, doesn't affect the other person, P3, until maybe a note gets passed under the door, P4 receiving the message. Until that note arrives, their actions are totally independent, concurrent.
Exactly. That's the essence of concurrency in this model. Okay, so now, building on this foundation of the happen before relation, Lamport introduces the core mechanism for tracking this. Logical clocks.
Logical clocks, not real clocks, right?
Definitely not physical timepieces. They're an abstract concept. Basically, a way to assign a number, just a simple counter value, really a timestamp to each event.
It's like putting a serial number on each event.
Sort of, yeah. But these numbers have a crucial property. The fundamental requirement for a correct system of logical clocks is what Lamport calls the clock condition.
The clock condition. Okay, what's that?
It's simple but powerful. For any two events A and B, if A happened before B, meaning AB, then the logical clock value of A must be less than the logical clock value of B. We usually write this as CA, CB.
Okay, so if A causally happened before B, its logical clock number must be smaller than B's number. The clocks have to respect the causal flow.
Precisely. The logical clocks must preserve the causal ordering defined by the happened before relation. They need to reflect the sequence of cause and effect.
That makes intuitive sense. If A causes B, B should happen at a later time, logically speaking.
Exactly. But, and this is a really important nuance, the converse is not required.
The converse, meaning if CA, CB, it doesn't automatically mean a B.
Correct. Just because one event has a smaller logical timestamp doesn't force a causal relationship. Concurrent events, for example, don't have to have the same clock value. They can have different clock values.
Oh, okay. So the clock condition is a one-way street.
Yeah.
Causality implies clock order, but clock order doesn't imply causality.
You got it. If we look back at figure 1 again, remember events P2 and Q3 were concurrent.
Right. No causal path between them.
Okay, now, within process P, P2 definitely happens before P3. P2, P3. So the clock condition demands CP2, CP3. Now, what if we also required that concurrent events must have the same clock value?
Then CP2 would have to equal CQ3.
Right, but if CP2, and we know CP2, CP3, then that would force CQ3 to be less than CP3.
Which sounds weird if key 3 and P3 are also concurrent.
Exactly. It creates contradictions. So the clock condition is only about preserving the known causal order. It doesn't impose any specific ordering requirement on concurrent events just based on their clock values. They can be ordered arbitrarily by the clocks as long as causality isn't violated.
Okay, that clarifies things. The goal is consistency with cause and effect, not forcing a total order just yet. So how do we actually implement these logical clocks to make sure they satisfy this clock condition?
This is where the elegance really comes in. Lamport provides two incredibly simple implementation rules, usually called IR1 and IR2. If processes follow these two rules, the clock condition will automatically hold true.
Use simple rules. Let's hear them.
Okay. IR1 is the internal clock update rule. It says, each process chi increments its local logical clock psi between any two successive events within that process.
So every time a process does anything locally, executes an instruction, performs a step, it just bumps up its own private counter.
Yep. If process pi has an event A followed immediately by event B, it must ensure that CC, CB. The simplest way is just C increments by at least one between A and B.
Okay, like taking steps, every step increments your personal step counter. That handles causality within a single process. Makes sense. What about messages?
That's where IR2 comes in, the message-based clock update rule. It has two parts. Part A. If event A is the sending of a message M by process pi, then the message M contains a timestamp 2 equal to C.
So when you send a message, you stamp it with your current logical clock time, like dating a letter.
Exactly. You put your current logical date on it. Then, part B. Upon receiving a message M with timestamp T, the receiving process PJ must update its own clock CJ. It sets CJ to be greater than or equal to its present value. ND also strictly greater than the message's timestamp T.
Whoa, okay, so when I get a message, I look at its timestamp, and I have to immediately adjust my own clock to be later than that timestamp.
Yes. The common way this is implemented to satisfy the clock condition robustly is for the receiver PJ to set its clock CJ to max current CJ value TAM plus 1.
So take the bigger value, either my current clock or the message's time, and add 1. That guarantees my clock jumps ahead of the sender's time when the message was sent.
Precisely. It ensures that the clock value at the receive event is always greater than the clock value at the send event, satisfying the second condition of the happen before relation send receive.
Wow, that's incredibly neat. These two rules, IR1 and IR2, they seem almost too simple, but together they weave this consistent fabric of causal time across the entire distributed system.
They do. It's really quite profound.
It's not about what some external stopwatch says. It's about creating a logical order based purely on the internal sequence of events and the actual flow of information via messages. A distributed system learning about its own past.
And you can visualize the effect of this. Think about figures 2 and 3 in the paper. Figure 2 shows our wavy space-time diagram again, but now it adds tick lines, lines connecting events across different processes that have the same logical clock value.
So all the events with logical time 5 are connected by a line, all the 6s, and so on.
Right. And these tick lines will generally look jagged because processes update clocks at different rates and based on message arrivals. But the beauty, shown in figure 3, is that you can conceptually redraw the space-time diagram, stretching and squashing the time axis for each process so that all these tick lines become straight horizontal lines.
Ah, like you're imposing the logical clock's grid onto the diagram.
Exactly. It demonstrates visually that this system of logical clocks provides a perfectly valid coordinate system for the events in the system. It's just as valid a representation of time for ordering purposes as any other, and crucially, it doesn't need any concept of physical time to achieve this consistent ordering based on causality.
Okay, so we've got a way to establish a partial order using the happen before relation, and we have these logical clocks ensuring causal consistency, CACB, if a B. But you mentioned earlier, sometimes partial isn't enough. Sometimes you need everyone to agree on a single, unambiguous order for all events, right?
That's right. For many practical applications, think resource allocation like that airline seat, or managing updates in a distributed database, or even validating transactions in a blockchain, you need a definitive total order. You need to be able to compare any two events, A and B, and say definitively whether A came before B or B came before A in this agreed upon total order, even if they were concurrent according to the relation.
So how do we get from the partial order to a total order? We
Right.
need to somehow resolve the ambiguity of those concurrent events.
Lamport's solution is, again, remarkably simple and effective. He shows how to extend the partial ordering into a total ordering, let's call it, read as fully proceeds, by simply adding an arbitrary but consistent tie-breaking rule.
A tiebreaker for concurrent events. How does it work?
The rule is this. For any two distinct events, A occurring in process pi and B occurring in process pj, we say A fully precedes B if either one of two conditions holds.
Okay, condition 1.
Condition I. The logical clock value of A is less than the logical clock value of B, CJB. So if their logical clocks already give them a distinct order, we just use that order. Simple enough.
Right, if CA is 5 and CB is 7, then A comes before B.
Exactly. But what if they have the same logical clock value, CA, CJB? This could happen for concurrent events.
That's the tie. How do we break it?
Condition 2. If psi A equals CJB, then we use an arbitrary predetermined total ordering of the process IDs themselves. We just assign a unique number or name to each process, like P1, P2, P3, and decide beforehand on a fixed order, for example, P1, P2, P3. If the logical times are tied, we say AB if the process ID of A pi is less than the process ID of B, Pj, according to this fixed ordering.
Whoa. So if event A and P1 and event B and P2 happen at the exact same logical time, say 10, we just look at the process IDs.
Right.
Since P1, P2, we declare that A fully precedes B in our total order.
Precisely. It's an arbitrary choice in terms of causality, but it's consistent. Everyone using this rule will always break ties the same way, resulting in the same total ordering of all events across the entire system.
That seems deceptively simple. But the implication is huge. It means the system can now definitively decide who went first for any pair of events,
Right.
even if their logical clocks thought they happened simultaneously. It's like having that race referee who, if two runners cross the finish line at the exact same logical moment according to the clock, just looks at their pre-assigned lane numbers to decide who gets the gold.
That's a perfect analogy. It provides a deterministic, unambiguous, system-wide sequence for every single event. And this total ordering is the key that unlocks solutions to many distributed coordination problems.
Like the one you mentioned earlier, distributed mutual exclusion.
Exactly. The paper uses distributed mutual exclusion as a prime example to illustrate the power of this total ordering achieved with logical clocks.
Okay, let's dive into that. Remind us of the problem first.
The problem is classic. You have a single shared resource. Maybe it's a printer, maybe it's exclusive access to update a specific record in a database. Maybe it's a critical section of code that only one process can execute at a time.
Right, something that can't be used by multiple processes simultaneously without causing issues.
Correct. And you have many different processes in your distributed system that might want to access this resource. The challenge is, how do they coordinate among themselves to ensure only one process uses the resource at any given time, and that access is granted fairly?
So what does fairly or correctly mean here? What are the requirements for a good solution?
The paper lists 3 essential conditions for a correct distributed mutual exclusion algorithm.
A process granted the resource must release it before it can be granted to another process. Obvious, only one at a time.
Okay, no sharing.
Second, different requests for the resource must be granted in the order in which they are made, according to our happened before relation. This ensures fairness based on causality.
First come, first serve, based on the causal order.
Right. And third, if every process that is granted the resource eventually releases it, no process holds it forever, then every request for the resource is eventually granted. No starvation. Everyone who asks eventually gets a turn.
Okay, those 3 conditions seem necessary. Now, my first instinct, again, is why not just have a central coordinator, a single process that handles all requests and grants permission? You mentioned earlier this can fail. Can you walk us through that distributed system gotcha again? Why doesn't a central bouncer always work?
Right. It seems intuitive, but Lamport points out it often fails to meet condition 2, granting requests in the order they were made, unless you make extra, often unrealistic assumptions about message delivery. Here's the scenario he describes. Suppose process P1 wants the resource. It sends a request message to the central coordinator. Let's call it P0.
Okay, P1 asks P0.
Immediately after sending that request, P1 sends a completely separate message to another process, P2. This message could be about anything, it doesn't matter.
P1 talks to P2 after asking for the resource.
Now, upon receiving that message from P1, process P2 decides it wants the resource too. So P2 sends its own request message to the central coordinator P0.
Okay, so P2 asks P0, but only after hearing from P1.
Correct. Now, here's the gotcha. Due to network delays being unpredictable, it's entirely possible for P2's request message to arrive at the central coordinator P0 before P1's original request message arrives, even though P1 initiated its request sequence first.
Ah, so P0 sees P2's request first, even though P1's request happened before. P2's request in the causal sense, P1 requests, P1 sends to P2, P2 receives, P2 requests.
Exactly. If P0 simply grants the resource based on the arrival order of requests at P0, it would grant it to P2 first, violating condition 3. The central coordinator doesn't have enough information about the true causal happened before ordering just by looking at when messages arrive at its doorstep.
That's the classic trap. Relying on arrival order at one point doesn't respect the distributed causal order. Lamport really nailed that issue.
He did, and his solution is brilliant because it's fully distributed. No central coordinator.
Yeah.
It uses the logical clocks and the total ordering we just discussed. Each process runs the same algorithm and makes decisions based on its local information and the messages it exchanges.
Okay, so how does this distributed algorithm work? No bouncer, just rules everyone follows.
Right. Each process maintains its own request queue locally. This queue stores resource request messages it knows about, its own and others, ordered according to the total ordering. Remember, uses logical timestamps first, then process IDs as tiebreakers.
Everyone keeps their own ordered list of who wants the resource.
Yep. Now, here are the 5 rules of the algorithm.
Requesting the resource. When process pi wants the resource, it first increments its own logical clock psi, then it sends a pi requests resource message, timestamped with this new psi value, to all other processes. It also adds this message with its timestamp to its own local request queue.
Okay, announce your request, everyone. Timestamp it and put it on your own list.
Got it. Rule 2. Receiving a request. When another process, say PJ, receives that pi request resource message with timestamp tpi, PJ first updates its own clock CJ using the max CJ tpi plus 1 rule. Then it places pi's request message onto its own local request queue, maintaining the order. Crucially, PJ then sends a timestamped acknowledgement message back to pi.
Ah, the acknowledgement is key. So pi knows that PJ has received and queued its request. It confirms the message got through and was processed.
Exactly. It's vital for ensuring pi knows its request is globally acknowledged eventually. Now, rule 3. Releasing the resource. When pi is done with the resource, it removes its own request message from its local queue, then it increments its clock again and sends a timestamp pi releases resource message to all other processes.
Tell everyone you're done.
Rule 4. Receiving a release. When process PJ receives a pi releases resource message, it updates its clock based on the message timestamp and then simply removes pi's corresponding request message from its own local queue.
Okay, update the local queue based on release messages. Makes sense. Now for the magic part. How does a process actually decide to enter the critical section to use the resource?
This is rule 5. Granting the resource, the clever part. Process pi grants itself the resource and enters the critical section only when 2 conditions are both met.
2 conditions. Okay, what's the first one?
First, 1. Pi's own request message must be at the front of its own local request queue, according to the total ordering. In other words, based on all the requests Pi knows about, its own request has the earliest timestamp, with ties broken by process ID.
So I have to be first in my own line, according to the global ordering rules.
Precisely, but that's not enough. Here's the second critical condition, too. Process Pi must also have received some kind of message. It could be another process's request, an acknowledgement to its own request, or a release message from every other process in the system where that message has a logical timestamp later than the timestamp of Pi's own request.
Whoa, okay, wait, let me unpack that. I need my request to be first in my queue, and I need to have heard from everyone else with a message time-stamped after my request. Why is that second part necessary? It sounds like waiting for everyone to catch up.
It is exactly about ensuring everyone has caught up, logically speaking. Condition 2 is the genius part. It guarantees that Pi cannot grant itself the resource until it knows that every other process is aware of its request or aware of some event that happened after its request. Why? Because if PJ hasn't sent a message with a timestamp later than Pi's request, Pi cannot be sure that PJ doesn't have an earlier request, according to Twitter, that simply hasn't arrived at Pi yet due to network delay.
So by waiting for a later time-stamped message from everyone, Pi confirms that nobody else has an older, more prioritized claim that Pi just hasn't heard about yet. It ensures Pi has a sufficiently up-to-date view of the global request queue state before proceeding.
Exactly. It ensures that when Pi grants itself the resource, because its request is first in its queue, condition 1, that decision is stable and correct because it has received confirmation, condition 2, that all other processes have progressed logically beyond the point of Pi's request. It prevents Pi from jumping the gun based on incomplete information.
That is brilliant. It's a truly distributed consensus achieved just through these message exchanges and timestamp comparisons. No central server, no single point of failure. Each process follows the rules, uses the total ordering, waits for that crucial confirmation from everyone else, and then knows when it's safe to proceed.
Precisely.
It's like that symphony conductor again. They don't need to see everyone finish the previous bar. They just need a signal from each section confirming they've received the instruction for the next bar, a message with a later timestamp before giving the downbeat. Everyone keeps pace based on the exchanged messages and the shared understanding of logical time. What a powerful algorithm. When you first encountered this, was this the bit that made you go, aha?
For me, it absolutely was Rule 5, especially Part 2. That condition, the waiting for later timestamped messages, it just clicked. It showed how you could build certainty and global consistency from purely local information and message exchanges, realizing that you don't need a central authority if every participant can independently verify a consistent view of the relevant past based on these timestamped messages. That was a genuine aha moment. It fundamentally changes how you think about designing coordination in distributed systems.
It really does. It feels like unlocking a secret to distributed harmony. And the paper suggests this isn't just for mutual exclusion, right? This whole state-machine idea.
That's right. Lamport points out that this approach, using logical clocks and the resulting total ordering, can be generalized to implement any kind of desired multi-process synchronization. The core idea is to have the processes simulate a state machine.
A state machine, like states and transitions.
Exactly. Think of it as a deterministic program. It has a set of possible states, and it receives a sequence of commands. Each command causes a transition from one state to the next. Now, in a distributed setting, different processes might issue commands.
How do they stay in sync?
By using the total ordering, all processes use the algorithm, like the mutual exclusion one, but generalized, to agree on the exact same sequence of commands. They might receive command messages in different physical orders, but they use the timestamps and the total ordering rule to sort them into one identical sequence.
So everyone processes command 1, then command 2, then command 3 in that exact same order.
Yes. Since the state machine itself is deterministic, the same command in the same state always produces the same next state, and every process executes the commands in the exact same order, they will all independently compute and maintain the exact same state for the simulated machine over time.
Wow. So this wasn't just about, sharing a printer fairly. It was effectively a blueprint for building complex, consistent, reliable, distributed systems of any kind. Anything where multiple parties need to agree on a shared state or a sequence of events.
Absolutely.
That's mind-blowing. Think about the implications.
Yeah.
Distributed databases, replicating transactions, they need to apply those transactions in the same order everywhere.
Crucial for consistency.
Or distributed ledger technologies, like blockchain. Everyone in the network needs to agree on the exact sequence of blocks, the exact order of transactions within them. This total ordering mechanism seems tailor-made for that kind of problem. It provides a mathematical foundation for achieving decentralized consensus on a shared reality.
It certainly laid the groundwork for many of those later systems and protocols. It provided the conceptual tools.
So no more blaming the internet lag for losing my online game. It's all just these beautifully synchronized logical clocks.
Yeah.
Or maybe not so synchronized if I'm losing.
Well, while the logical clock system and the total ordering are incredibly powerful, they do have a significant limitation, which Lamport himself addresses very clearly. It's what he calls the anomalous behavior problem.
Anomalous behavior, meaning
Yeah.
weird stuff happens.
Meaning the logical order the system creates might not match what a human user perceives as the real-world order of events, especially when external actions are involved.
Okay. This sounds like we need to revisit our phone call example to really drive this home.
Yes, let's do that. Remember, you're in City A. You make a request to a computer system. Let's call that event A. It gets a logical timestamp, say CA, IL10.
Okay, event A at logical time 10.
Then you immediately pick up the phone and action outside the computer system and call your friend in City B. You tell them, hey, make a request for me. So your friend makes a request to a different computer system, event B.
Okay, the phone call caused event B.
Right.
In the real world, A happened, then the call, then B. So A physically happened before B.
Right. That's the user's perception, the physical reality. But now think about the system's logical clocks. Maybe due to network delays when event A's messages were propagating, or maybe just because of the arbitrary process ID tie-breaking, it's entirely possible that event B gets assigned a logical timestamp earlier than event A. Maybe CB equals 8.
Wait, so the system's total order would say BA since 8, 10, even though in reality A happened before B.
Exactly. From the system's perspective, it didn't see the phone call. The phone call was an external event, invisible to its internal relation. It just saw two requests, A and B, possibly concurrent or ordered logically based on message timings and tiebreakers, and it assigned timestamps. The resulting total order BA feels completely wrong or anomalous to you, the user, because it violates your understanding of the real-world causal chain involving the phone call.
The system's internal reality doesn't match the user's external reality because the system doesn't know about the external causes.
Precisely. The source of the problem, as the paper clarifies, is that the logical happened before relation is only defined for events within the system message sends, receives, local actions. External events, like that phone call, are simply not part of its universe. The user's perceived happened before, let's call it, physical happened before, is a stronger relation that includes these external influences. The purely logical system, operating only on internal events, has no inherent way of knowing about or respecting this stronger relationship.
Okay, so this logical ordering is great for internal consistency, but it can lead to weird results for users if external actions are involved. How do we fix this? How do we avoid these anomalies?
Lamport outlines two basic approaches. The first one basically puts the burden on the user or the application programmer. The system could, say, return the timestamp TA when event A occurs. Then the user, or the application acting on the user's behalf, initiating event B, would have to explicitly tell the system, hey, make sure event B happens after timestamp TA. You'd have to manually carry the time dependency across the external channel, like the phone call.
That sounds cumbersome and probably error-prone for most situations. People won't remember to do that.
Exactly. It's generally impractical. So the second and much more common approach in practice is to bring physical clocks back into the picture, but in a very specific way. The goal is to build a system where the clocks satisfy what Lamport calls the strong clock condition.
Strong clock condition. Okay, what does that require?
It requires that the system's clocks, which will now be based on physical time, though perhaps adjusted, must reflect the real-world causality, formally. For any two events, A and B in the system, if A physically happened before B, AB, including any external influences like our phone call, then the clock value assigned by the system to A must be less than the clock value assigned to B.
So the system's clocks must tick in a way that respects the actual real-world flow of events, even the ones happening outside the system.
That's the goal. If we can achieve that, then anomalous behavior disappears because the system's ordering will align with the user's perceived ordering.
Okay, so now we're back to physical clocks. What do we need from them to achieve this strong clock condition?
This is where we shift from the purely abstract logical clocks to the messy reality of physical clocks. Lamport states two conditions that these physical clocks need to meet reasonably well. First, PC1, the clock rate condition. This basically says that each physical clock, where is real physical time, must run at approximately the correct rate. Its rate of change, dCA/dt, should be very close to 1. The paper specifies dCA to 1 kappa, where kappa, he uses kappa, not x, my mistake earlier, is a very small constant representing the maximum drift rate.
So your clock shouldn't tick significantly too fast or too slow compared to real time. It needs to keep pace reasonably well. Like my watch shouldn't gain or lose minutes every hour.
Exactly. For typical crystal-controlled clocks and computers, this kappa is tiny, maybe on the order of 10.6, so they're pretty good, but not perfect.
Okay, that's PC1. Clocks need to run at roughly the right speed. What's PC2?
PC2 is the clock synchronization condition. It says that the clocks of any two processes, I and J, must be kept synchronized with each other. The difference between their readings at any given real-time T should be bounded, CJT epsilon, where epsilon is some small positive number representing the maximum allowed skew between clocks.
So not only do they need to tick at the right rate, PC1, they also need to be reasonably close to showing the same time, C2. We need to prevent them from drifting too far apart from each other.
Correct. We need both bounded rate drift, kappa, and bounded skew, epsilon.
And how do these relate back to avoiding those weird anomalies from the phone call example?
Lamport shows the mathematical relationship. To satisfy the strong clock condition, and thus avoid anomalies, the system needs to maintain its physical clocks such that epsilon, 1 kappa, is less than or equal to mu. Here, mu is the shortest possible time it takes for a message to travel between any two processes involved in the relevant external event chain, like the time for the request message in our phone call example.
Whoa, okay. Epsilon, max skew, divided by 1 kappa, related to min clock speed, has to be less than mu, shortest message delay. That links clock accuracy and synchronization directly to the network physical properties.
It does. It essentially says, if your clocks drift too much, epsilon is too large, or if they run too slowly, kappa is too large, making 1 kappa small, then even a very fast network, small mu, might not be able to propagate information quickly enough to maintain the correct real-world ordering perceived by the user. Your clocks need to be good enough relative to your network speed to avoid anomalies.
That makes sense. If my clock is way off, knowing the message arrived quickly doesn't help me order things correctly relative to real-world events. So how do we achieve this synchronization? How do we keep epsilon small in a real system?
This leads Lamport to present specialized versions of the logical clock implementation rules, IR1 and IR2 mints, but adapted for synchronizing these physical clocks to meet PC1 and PC2 approximately, and thereby satisfy the strong clock condition.
Okay, physical clock synchronization rules. What's IR1?
IR1 is pretty straightforward for physical clocks. For each process pi, its physical clock sign must always be running. DC date must always be greater than 0. Basically, the clock must always advance forward when the process is running. It shouldn't stop or run backward unless it's being explicitly reset, for example, by a message correction.
Clock's got to tick forwards. Got it. What about IR2 ones, the message rule?
IR2 is where the synchronization happens, and it's subtly different from the logical clock version. Part A, if process pi sends a message M at physical time T, then M contains the timestamp TM, explorer CIT. So just like before, you stamp the message with your current physical clock reading when you send it.
Okay, same as logical clock so far. What's different in part B, the receiving part?
Part B. Upon receiving message M sent at time T with timestamp TM, at physical time T, the receiving process PJ sets its clock CJ forward. It sets CJT to be the maximum of its current value, CJD meaning just before the update, or the sender's timestamp plus an estimated minimum delay. 10 plus mum.
Wait, team plus mum? What's mum? Is that the same mu as before?
It's related, but specific to the message, mmum represents a known minimum delay for that specific message M. It's the absolute shortest possible time that message could have taken to travel from pi to PJ. This is a crucial detail.
So unlike logical clocks where we just did team plus 1, here the receiver uses knowledge of the minimum possible physical transmission time to make a more informed adjustment.
Exactly. The receiver PJ thinks, okay, I received this message now at my time CJ. It carries timestamp team from the sender. I know the fastest this message could possibly have gotten here is mum. Therefore, the sender's clock C must have read team no earlier than my current time minus mum. To be safe and potentially pull my clock forward if it's lagging, I should set my clock to at least team plus mum. It uses the minimum delay to estimate a lower bound on the current real time at the sender relative to the timestamp received.
That's clever. It uses a physical property, mum, to help synchronize the physical clocks.
Yes. And critically, there's an unstated but vital constraint Lamport mentions later. Clocks are never set backwards. If this calculation, Tm plus mum, results in a time that is earlier than PJ's current clock, Suj, then PJ just ignores the update and lets his clock continue ticking forward. It only performs the adjustment if Tm plus mum is later than its current time.
So clocks only ever jump forward to catch up, they never jump backward. That avoids creating confusing time warps.
Precisely. It maintains consistency, although it complicates proving how tight the synchronization epsilon can be.
Speaking of which, does Lamport give any guarantees about how well this synchronization works? How small can we keep epsilon using these rules?
He does. He provides a significant synchronization theorem later in the paper, which gives an upper bound on the maximum skew epsilon that can occur between any two clocks in the system when using this algorithm, IR1 and IR2.
A mathematical guarantee on clock synchronization. What does it depend on?
The theorem relies on a few reasonable assumptions about the system. First, the network of processes needs to be strongly connected, meaning messages can eventually get from any process to any other, perhaps indirectly through intermediate processes.
Okay, no isolated parts of the system.
Second, there's a maximum time interval, let's call it tau, within which messages are sent over every communication link in the network path needed to achieve synchronization. Basically, processes need to communicate reasonably often.
Keep the chat lines open.
And third, the unpredictable part of the message delay, the delay beyond the minimum mum, is bounded by some value, let's call it psi. Network delays aren't infinitely variable.
Okay, connected network, regular communication, bounded delay variation. Seems plausible. What's the result?
Under these assumptions, the theorem states that the maximum clock skew epsilon between any two processes is bounded. The bound depends roughly on the network's diameter d, the longest shortest path between any two nodes, the clock drift rate kappa, the message sending interval tau, and the delay variability psi. The formula is approximately epsilon oppels d2 kappa tau plus psi.
Wow. So the maximum difference between clocks depends on how big the network is, how inaccurate the clocks are, how often they talk, and how jittery the network delays are.
That's it.
That's the engineer's guarantee right there.
Sir.
It tells you quantitatively. Here's how closely you can keep your clocks synchronized in a real distributed system, given its physical characteristics and the slight imperfections of reality. It's like saying, okay, your watches might not be perfect and the mail might be a bit unpredictable, but if you talk to each other every hour across this city, diameter d, we can guarantee your watches will never be more than epsilon seconds apart. It moves synchronization from a vague hope to a concrete, measurable, and achievable engineering goal.
Exactly. And the paper notes that deriving this bound, especially under the constraint that clocks are never set backwards, was a non-trivial result at the time. It provided a solid theoretical foundation for practical physical clock synchronization algorithms.
This is amazing stuff. It feels like we've gone from the abstract philosophical problem of time in distributed systems through logical clocks for internal consistency and arrived at practical methods for synchronizing real physical clocks to avoid user confusion and provide concrete guarantees.
That's the arc of the paper, yes. It connects the theoretical foundation to practical implementation.
And looking beyond just keeping time, you mentioned this state machine idea enabled by the total ordering. It feels like the impact of this paper goes way beyond just mutual exclusion or time itself.
Oh, absolutely. The concepts laid out here, partial order, logical clocks, total ordering, the state machine replication idea, they become fundamental building blocks for decades of research and development in distributed systems.
It provided the language and the tools.
Exactly. But Lamport is also careful to point out the limitations. We talked about the anomalous behavior with purely logical clocks, and for the generalized state machine approach.
Yeah, you mentioned a limitation there too.
Yes, the basic state machine replication approach described relies heavily on the active participation of all processes. If one process fails, crashes, gets disconnected, the whole system can grind to a halt. Why? Because other processes might need to receive a message from the failed process to establish the correct total order or to satisfy condition of the mutual exclusion algorithm, hearing from everyone. If that message never comes,
the whole system gets stuck waiting.
Right. And here Lamport makes another profound observation. The very concept of failure is deeply intertwined with physical time.
How so?
Think about it. If a process stops sending messages, how do you know if it has failed, crashed, or if it's just pausing for a really, really long time, or if the network connection is just incredibly slow? Without some notion of expected physical time, I should have received a response within 5 seconds. You can't reliably distinguish a catastrophic failure from a temporary delay or pause.
So a user knows a system crashed because they got tired of waiting.
Yeah.
It's our perception of physical time passing that defines failure from our perspective.
Precisely. The paper doesn't solve fault tolerance directly, but it acknowledges this deep connection. It implicitly points towards the need for mechanisms like timeouts, based on physical time, to handle potential failures. He actually refers to later work needed to handle this, and indeed, Lamport himself went on to develop seminal algorithms like Paxos, which do address fault tolerance in distributed consensus, building upon these foundational ideas of ordering and time.
It's like this paper laid the perfect groundwork, defining the core problems and solutions for an idealized world, and then opened the door for tackling the messier realities of failure.
That's a great way to put it.
Looking back on this whole deep dive, the enduring legacy of this 1978 paper is just immense, isn't it?
Yeah.
It feels like it fundamentally shifted how computer science thought about time and order in these increasingly complex systems.
It absolutely did. It moved the field away from relying on vague, intuitive, and often incorrect notions of shared global time and towards a rigorous, mathematically sound, causal framework. It gave us the vocabulary and the concepts to reason precisely about event ordering in asynchronous, distributed environments.
This exploration of Lamport's work really highlights a foundational concept that, as you said, underpins so much of our modern digital world, often invisibly. Cloud computing, databases, blockchains. They all wrestle with these issues of time and order. It's a fantastic example of how deeply theoretical computer science can have incredibly practical, real-world consequences.
It really is.
And the core idea, the big takeaway for me, is his paradigm shift. It's not primarily about synchronizing clocks to some perfect universal real time, because that's often impossible or impractical in a distributed system. The real goal is to first establish a consistent order of events based on causality that all the machines within the system can agree upon using mechanisms like logical clocks. And then, only then, do we worry about how that internal consistent order relates to human perception and real-world physical time, bringing in synchronized physical clocks if needed to bridge that gap and avoid those anomalous behaviors.
That's a perfect summary of the core philosophy. Define internal consistency first, then relate it to external reality. So let's quickly recap our journey today. We started with that fundamental, almost philosophical problem. How do you define what happened first in a distributed system where messages are delayed and there's no central clock? We saw how physical time is unreliable for this and intuition breaks down.
Right. Then we dove into Lamport's elegant solution.
Mhm.
They happened before relation, based on causality, and the invention of logical clocks, IR1, IR2, to track this partial order consistently.
We then saw how this partial order could be extended into a crucial total ordering, using timestamps and a simple tie-breaking rule. And we explored how this total ordering enabled a fully distributed algorithm for a classic problem like mutual exclusion, using that clever five-rule approach.
But we also hit the limits, the anomalous behavior problem, where the system's logical order might clash with real-world perception due to external events.
Which led us back to the need for physical clocks, but used carefully. We looked at the strong clock condition, the requirements for physical clocks, PC1 rate, PC2 synchronization, and Lamport's algorithm, IR1, IR2, and theorem for keeping them synchronized within measurable bounds, epsilon.
And finally, we touched on the broader implications, state-machine replication for general distributed consensus, and the deep connection between failure detection and physical time. So the next time your online game feels perfectly in sync, or maybe a financial transaction happens instantly across continents, just take a moment to remember the silent, incredibly complex dance of logical and perhaps physical clocks happening behind the scenes. This intricate choreography, ensuring a consistent reality that no single computer can fully grasp on its own, is built on ideas like the ones Lamport laid out. It really makes you wonder, doesn't it? What other fundamental assumptions do we hold about the world, maybe even about concepts simpler than time, that might need a similar deep dive to be truly understood in our increasingly interconnected and distributed reality?
It's a fascinating question. We hope this deep dive has given you a fresh perspective on how something seemingly simple like time becomes incredibly complex, subtle, and critically important when viewed through the lens of distributed computer systems. We definitely encourage you to explore more of Leslie Lamport's work. He's a giant in the field. Or, if you're feeling adventurous, maybe even dive into the original 1978 paper itself. It's dense, but truly rewarding.